First thing is there's nothing quantum in my talk, but there is vortex dynamics, turbulence, and 2D. So I'm kind of qualified, I guess. Sorry, this doesn't work. Okay, so there's a lot of reasons why we need to study particulate flow and turbulence in particulate flows. And because there are quadrillions of particles in these flows, it's very, very difficult to do simulations where we need to, follow each particle individually. But in these regions of extreme clustering, we'll need to do that. So that's the point I want to talk about. And there is a need for methods which can do this for very large numbers of particles. So the flow that we'll be talking about is as follows. We have a very, very high Reynolds number for the flow. So this is the flow with its velocity u. We have a very, very small Reynolds number for the particles which are embedded in the flow. So the particles are in dilute suspension. They're all spherical of radius, very tiny radius a. There's a relative velocity q between the particle velocity and the flow velocity, and the particle Reynolds number is in terms of this relative velocity. So like we're talking about this thing under one-way coupling, by which you can imagine something like bacteria in the ocean or viruses in the ocean. The ocean tells the viruses where to go, but the viruses don't do anything to the ocean. So that is a summary of one-way coupling. So the fluid is just dictated by the Navier-Stokes equation with incompressibility. The particles, on the other hand, because they're of small Reynolds number, they're in unsteady Stokes flow. So the Gatineau-Maxey-Riley equation, which we will call GMR, it models what the particles do. So the position of the particle is determined by its velocity. The velocity of the particle, remember this is a relative velocity, is governed by this unsteady Stokes equation, the GMR. So in this equation, there is this complicated force called the Bassett-Boussinesq history force. So just to get an idea about how I should describe it, how many of you are familiar with the Bassett-Boussinesq history? Okay, some but not all. Okay, so this force is a very complicated force to handle. As you can see, there is a 1 over square root t which gives you a singularity at 0 time. There is this horrible integral where for every individual particle, from time equal to 0 to now, we have to perform this integral of the relative acceleration with this kernel, 1 over root t kernel. So like for every particle at every time, I have to go all the way back to time equal to 0. That's how it is. Okay, so we can also, it's much more common to solve another equation where you just take the old GMR and drop the Bassett-Boussinesq history term, and we will refer to this as the baby GMR, which is actually easy to solve because you've actually neglected all the problems away. And in this flow, there are two important parameters. One is the R, which is a measure of the density ratio of the particle to the fluid, and the other is the Stokes number of the particle, which is a measure of the relative the response time of the particle to the time scale of the fluid. And we'll remember that when R equal to 0, we're talking about infinitely dense particles, and R equal to 1 would be neutrally buoyant particles. We're going to be considering both of these today. So in the case of a heavy particle, I'm just going through this nice derivation which makes life easy. You can actually at small Stokes expand the baby GMR, and you can get an expression like this, which you can rewrite like this. And up to order 1 in Stokes, you can actually write the particle velocity just in terms of the flow. So you do not need to solve for each particle. So if you know the flow velocity and you know everything about the flow, then you know everything about the particle, you know its velocity. So this is a very nice reduction you can make at small Stokes. But there are conditions which apply, and the conditions which apply are about extreme clustering. So whenever particles come together a lot and they start colliding against each other, then this kind of field description for the particle velocity will fail. So that's what we will talk about. Okay, so when we talk about clustering, like we need clustering for a variety of situations. So I need not go into that. Okay, so what is the basic dogma of particulate flow? The basic dogma of particulate flow is that when you have particles which are denser than the fluid, then like you put these particles in turbulence, they're going to evacuate regions of vorticity because they're going to centrifuge out and they're going to collect in regions of strain. So this is the standard dogma, and this is a nice movie by Jason Picardo which shows that happening. So you see the particles which were uniformly distributed are now like evacuating the vortical regions and they're collecting in the strain regions. So like in fact at small Stokes number, using the arguments that I said earlier. So like what happens at small Stokes? So yeah, so one thing we want to do is that we want to look for regions where del dot V is less than 0. That implies clustering into an area, right? The particle field is very compressible. So we're going to look for places where del dot V is less than 0, which implies clustering. And we have to go to del dot V going towards minus infinity for extreme clustering, where everything goes into little, geometries of lesser dimension than the basic dimension. That's what we're looking for. And in this kind of flow at small Stokes, you can actually show very clearly that del dot V can be rewritten as this quantity where this is the strain tensor and the vorticity tensor. Yeah, so in regions of vorticity, you will see that this term doesn't come in and the minus and minus go away and del dot V has to be positive. So you can actually show that regions of vorticity have to be regions in which the particles will evacuate. Okay, and in fact, like you can write a simple equation for a single particle which will execute a Fermat spiral in this neighborhood of a single vortex. However, in a rotating frame, we need to revisit this dogma. And that's because the previous equation we wrote down gets modified by the base rotation of the background rotation of the system we are sitting in. And that can overpower things, and even in regions of vorticity, you can have clustering. So this is the first thing I want to talk about, which is that even in the vicinity of a vortex, so long as there's a background rotation or you're sitting in some kind of rotating frame, you can have clustering. And we're going to show that it can actually be extreme clustering where del dot V goes towards minus infinity. And the simplest rotating system you can imagine, at least we could imagine, was two identical vortices of circulation gamma separated by D, and they keep going around in a circle in inviscid flow. So this is what they're going to execute all the time, and this is the work of present PhD students Saumav and Divya. So we took this system, and first you can put passive particles in the neighborhood of these vortices. Now in the frame which is rotating with the vortices don't go anywhere. They're always going to sit here. So we've got fixed vortices for all time for the rest of the talk. So they sit here in the rotating frame, and you're putting particles in anywhere on one of these circles, then the particles will live on that circle forever so long as they're tracer particles. This is a well-known result where the trajectories of passive particles, they execute Cam-Tori around in the neighborhood of the vortices. Now, instead of the passive particles, we are putting particles of finite Stokes number. So that means they are inertial. They're in unsteady Stokes rather than plane Stokes. And so you'll see that depending on the Stokes number, all the particles who started out in this purple regime are going to be trapped forever in the neighborhood of the vortex. In fact, there'll be one point there which is an attracting fixed point, and all these particles are going to go to that particular fixed point and live there forever and ever. And as you increase the Stokes number beyond like actually a smallish value, you will see that such trapping doesn't happen. So this trapping happens only for very, very small particles. Now, this was for heavy particles, which meant infinitely dense compared to the fluid. Now, if you have particles which are finitely dense compared to the fluid, so this is important in the ocean, and we're mainly worried about like plankton in the ocean, or things which are carbonaceous material which is sinking in the ocean and going through turbulence. So such particles, so R equal to 0.84 means the particle is around twice as dense as the fluid. So they execute this kind of thing. It's a bit different from there, but this can happen at higher Stokes. That's the basic summary, that there can be a lot of trapping of everybody who started out in this neighborhood, and it can extend to higher Stokes. So this is a summary of what happens there. In the case of a heavy particle, we've seen only clustering all onto one point, and that happens for small Stokes number with this. And I've said without BBH, without Bassett-Boussinesq history, because we're still talking about baby GMR. So then, like, everything goes and gets trapped inside one attracting fixed point. At a higher Stokes number, you get limit cycles rather than attracting fixed points. And these limit cycles can go through this period doubling bifurcation towards chaos. So this is like a chaotic trajectory. So depending on the Stokes number, you can actually get these particles executing chaotic trajectories in some kind of strange attractor. So these are also extreme clustering, because the final dimension of the attractor is much less than 3. So like these are in extreme clustering, but this is what happens. And beyond a certain Stokes number, they leave the vicinity. So far, what have we got? We basically have two vortices going round and round, and we're looking at particles in the neighborhood, extremely simple. And then we see this unexpectedly complex behavior as a result. Now we add Bassett-Boussinesq history. The first thing is, like, I can no longer think of it as a field. I have to worry about, and there's many worries which we can't go into right now for the computation, but Vishal Vasan, our colleague right here in ICTS, has come up with some brilliant ideas on how to solve things with Bassett history without enormous memory storage for in the computer, as well as without enormous computational time, and with amazing accuracy. So that is explained in these papers. So we've used that technique to solve this problem, and now we include Bassett-Boussinesq history into the two vortex problem, and you see that there is an incomplete period doubling route to chaos. There is no chaos. So there's one period doubling, and then the whole thing stops. Particles escape, all particles escape, nobody gets trapped after this Stokes number. But notice that the Stokes number has practically doubled. So you can now have much bigger particles which get trapped near the vortex. So if you ignored Bassett history, you would be missing out this story. You would be missing out the fact that larger particles can actually get trapped in the vicinity of the vortex. So how many particles get trapped? This is the area of the basin of attraction. It's much higher with BBH than without. So that happens at a whole range of Stokes numbers. So then, like, what happens just this side and that side of the attractor? So at this attractor, you get a large number of particles being trapped, and just outside, you still have very large residence times of these particles as shown here. So the particles are slowly leaking, but still they spend enormous amounts of time in the vicinity of the vortex. So if you're looking for, situations like active living things coming closer to each other and being able to dash against each other, remember that in regions of extreme clustering, there's going to be extreme number of collisions. So these collisions are going to help in a variety of things like raindrops growing or planetesimal formation or things like that. So in that sense, like, even a slowly leaking thing is all right, because a lot of collisions can happen in this situation as well. We found some interesting things like period halving bifurcation when we change the density ratios. So in this little Stokes number regime, there's absolutely no trapping. And then you have period doubling, followed by halving. And that happens all the way from chaos to back as well. So, and with Bassett-Boussinesq history as well, we found some things, and these funny windows where nobody gets trapped. We have absolutely no explanation for this, except that the response is very nonlinear. It's nonlinear, though it's unsteady Stokes, because the particles depend on the flow velocity. The particle position depends on the flow velocity, and everything then depends on that. So this is just a summary of what I showed you. So there is density ratio on this side. This is heavy particles and this is neutrally buoyant particles, and there is Stokes number on that side. And you see there's a very strange response to Stokes number, which is very non-monotonic. This thing represents a fixed point. The black regions represent no trapping, and then limit cycle and more complicated limit cycles to chaos. So this is what this figure shows you. And this was the place where we looked at first the density ratio of approximately 2, where we had a period doubling route to chaos. And in this place, we had all the way to chaos and then period halving. And in this place, we had incomplete route to chaos and period halving. And after period halving, going back to an attracting fixed point. So the conclusions for this part are just this, that you can actually have large numbers of particles trapped near vortices, and these can show you these can display extreme clustering and actually go into objects of lower dimensions, such as an attracting fixed point or a strange attractor or things. There is a bizarre variation with Stokes, and Bassett history is important because if you drop it, you underestimate the Stokes number, you get many details wrong as well. And now let's just take the last few minutes to look at a completely different problem, which is active caustics. So in active caustics, so caustics are regions of extreme clustering where particles come together and there's, the number density diverges and there's large numbers of collisions. And if you did baby GMR, you can actually write down this equation, and this actually forms a singular perturbation problem. So what you need to know here is that if I look at the Stokes number and I say the Stokes number is so infinitesimally small, let me say we're considering only very tiny particles, and I throw away this term and I say U is equal to X dot, then I'm going to be in deep trouble because this is a second order equation which I've made into a first order equation. And that's the essence of singular perturbation, which means that however small the Stokes number, it's going to be important somewhere or other. And in particular, in the vicinity of a vortex, it's very important in this place. So this place near the vortex actually acts as a boundary layer. There's a special radius around every vortex inside which particles should not be treated as, inside which caustics can happen. So particles should not be treated as a field, and this singular perturbation becomes very important. So like this pink circle can actually overtake the black circle within that boundary layer. So like we're now going to talk about particles which have activity. These are like proxies for living things, and they don't have any inertia whatsoever. So the Stokes number is 0 and the particle Reynolds number is 0. So they're living in steady Stokes flow. So how on earth will they display caustics or do any such thing? That's what we set out to understand. And this was primarily the work of Rahul Chajwa, who's now postdocing in Stanford, and present student Rajarshi. So here we have the velocity of the fluid particle. It's given by the velocity of the fluid and this quantity called AW. A is just some activity parameter, and W is basically the size of this particle. So you can imagine that these are particles which follow their nose, and how well they follow their nose is dependent on how long their nose is. That's a way to think about it. And their nose gets stretched out. They're like a dimer. The nose gets stretched out by the shear and gets plane rotated by the vorticity. So this is the important part. It gets stretched out by shear. So then these are called active Hookean dimers, and they are a proxy for some aspects of living organisms. So here are these living organisms who try to follow their nose, and that effectively gives them an inertia. So you can actually replace this equation in that and get this equation. What matters here is that you have like an acceleration term with a, something like an effective mass, which came out of nowhere. It came out of this, in fact. So basically you can have caustics like behavior from these particles who have no Stokes number. So in the neighborhood of a point vortex, you can actually write down some stuff analytically. Inertial particles look like this. These passive particles have some extra terms which come from their activity. Sorry, not passive. Active particles have extra terms which come out of this. It looks like a complicated mess, but all hope is not lost. We can, in fact, write this quantity Z, which is proportional to the divergence, the gradient of the velocity vector of the particles. And in this Z, we can look for where Z trace of Z goes to minus infinity. And that will be basically extreme clustering. So we can look for extreme clustering by solving this equation. We can do singular perturbation theory on these equations. And then we understand something, and then we can run a simple 2D turbulence simulation with these particles put in there in one-way coupling. And you see that at very small levels of activity, they're primarily homogeneously distributed, but at moderate activity levels, they've actually evacuated the vortex. So they're pretty much mimicking inertia, and they're collecting in the strained regions. And at high activity, that again gets mixed up. So here activity is behaving like Stokes number. At very high Stokes number in inertial particles, you would again get this. So like the conclusions from this part is basically that they can semi-mimic inertia. I wrote semi-mimic because there's many ways in which they're different, and that singular perturbation theory provides insight into this. So this is the summary of what I've been trying to tell you. So rotating systems offer new opportunities for extreme clustering. So even if you have dense particles and you're throwing them in 2D turbulence or in any kind of turbulence, if there's a base rotation, which often happens if two vortices are near each other, or in a whole range of situations, like on Earth, or sometimes you could have a low Rossby number flow as well, like in a rotating system. And in all of those systems, you can have extreme clustering of pretty dense particles, and this can be important in a variety of situations. And microorganisms who have no inertia and are not supposed to be doing these things, in our model, I've written our model because I don't know, how well living things mimic this. They participate in extreme clustering, and this extreme clustering is coming from mechanics. That's the important part. Like normally when we think of active particles, we say, oh, they decide, they go where their friends are, or they're doing things like that, and we think of clustering as being a voluntary activity. But this is actually not a voluntary activity. Mechanics just makes them extremely cluster. So that's the end of my talk. Thanks for your attention.
Thank you very much. Very nice. About the second part of microorganisms, so I'm not sure I catch the model. So they swim in one direction?
So they, okay, if there was no flow, then they would swim in one direction. But because there's no flow, their side, okay, let me go back to that equation. Where is it? Yeah. So if there was no flow, then like this L also comes from the flow. So suppose this all wasn't there, their size would just shrink back to 0. So if you stretch them out, they'll follow the nose for a while, but after a while they won't have a nose. So then they'll just come to a standstill.
Okay, but what is A in the equation above? Is it a matrix or is it a coefficient here?
Sorry, A.
Yeah.
Yeah, it's right now just a coefficient.
It's just
in this, yeah, okay. Yeah. So it's just a number.
W is the direction of swimming.
W is the direction of this. Okay. So basically, the particle is, in the direction of W, and W is like a spring, so it will relax back if you don't stretch it out by flow. So it needs flow to follow its nose.
Thank you. Which are, when is it that you can be that you can reliably ignore the Basse-Boussinesq history force? So which are the main conditions where you can, is it conditions on the floor, on the combination of the floor or the Stokes number?
So you're saying when is it going to be important?
Yeah, when is it, or the other way?
Yeah, so basically in very, very dense particles, the Basse-Boussinesq history term becomes unimportant. But as you go towards neutrally buoyant, like it becomes very, very important. So suppose you're thinking about cloud water droplets in a cloud, then Basse-Boussinesq history is unimportant. Whereas if you're thinking of anything in the ocean, like nothing is that much denser, then for those particles, Bassett-Boussinesq history is important. And it effectively comes out of something like an impulsively started plate. So if you solve for an impulsively started sphere, which is accelerating relative to the flow, you'll actually get this kind of term.